Hello, this is the second audio lecture for engineering ethics, and I'm happy to be talking to you this week about the embeddedness of ethics and politics into technologies using the example of algorithms. And our core reading, which we'll talk about a little bit later from Kramer et al., is about how, in a specific case in medical technology programming, the selections by the designers become political components of the technology. The other two little readings are just about finding issues. And the, the problem with trying to dig up a concept like politics and ethics within something we have general assumptions about, like technology, is we often don't have the perspective to see things. So you look at something like Will Knight's article or Laura Seidel's, and you are asked to take seriously a perspective that's different from yours. And we will be doing that today. All right, so in the previous slide, I said we were talking about how we can develop perspectives for understanding politics and technology, and this is several issues are going on here. One is we're talking about the general perspective of the class, drawing on science, technology studies, as well as traditional ethics. And we are also specifically picking up and recentering the discussion of non-neutrality, of the expectation of politics that Langdon Winter used. And in that sense, all we're doing is saying, instead of technologies in general, as we have before, but algorithms are political. And we want to keep in mind that we've talked about naturalization and assumptions, that what we expect may not be correct. Algorithms may seem neutral devices, but they are not. Remembering our definition of engineering, that we're trying to say that to engineer something is to produce an expected or known outcome according to plan and purpose, we want to keep that in mind, because what an algorithm is really a plan for a specific outcome. And this continues the discussion that begins with the founding of modern computing and IBM and the Holocaust. It continues the discussion of standards and the masking or making invisible of options, of choices, and of politics that happens with digitization and datafication. And in part the same way, when we talked about digitization and datafication, we said there were decisions or choices made in what components of the world, of complexity, of the messy stuff, becomes data. And that by privileging those things, we have an effect on what we conceive of as known. And one of the things that's particularly strong, whether we're talking about individual computers or networked computers on the internet, is that those background choices, the fact that our interface with the internet is tiny, the fact that software perceived through user interface is a very small component of the software running, all of those processes of making some components visible are in fact made possible by the back-end programming. And one of the central ways for programming to be done, and increasingly important in this particular way, is to use algorithms. There are a whole lot of kinds of algorithms. There are a lot of ways it's slightly different in different fields. Computer science would use a different language to talk about it, but basically what we want to start with is a fairly simple definition of an algorithm. An algorithm is a mechanism by which we receive or pursue an ending. That is, it is the plan in an engineering project. You have an input, information, activity, etc., and at the end you get the output. And the set of rules, the set of steps that are in between those two things to receive that output is the algorithm. And while it is possible to have both informal or formal algorithms, the nature of an algorithm is step by step, and it is directive. For instance, if you fail one step, you don't move on to the next. I mean, you could have a rule there that says how to respond to that, but if it actually doesn't fit, it doesn't move forward. And so one of the things that happens when we design algorithms, when we use algorithms, is that only that which fits with the mental model that the algorithm assigns is allowed to be perceived, is allowed to be pursued. And if you remember our discussion when we talked about Renix and Robinson, about the failings of mental models in ethics, especially the tunnel and trolley problem, the nature of those mental models meant that once you were aware, you became more and more familiar with that kind of linear thinking, it becomes harder to do otherwise. And it turns out that when you actually instantiate, when you build in or replicate that kind of linear processing into a material thing, like a computer, like a watch, like a cell phone, like a car, what you're really doing is producing an outcome based on that linear process. And so one of the things that we want to understand is that in any case, you could have one algorithm, you could have others. And by the nature of our definition of politics, that any decision, any technology that can produce winners or losers, some people would prefer one or the other, is going to be inherently political. And what it means to be an algorithm is often made complex by the fact that we pay attention to outputs and not to the process by which the output is received. And that means that there is a fundamental lack of transparency, arguably, for everybody except programmers with a particular interest in algorithms. Even programmers who are working on computers will often use algorithms that are standardized without really reconceiving them. And it is not necessarily our goal to say that there is an ethical demand that every time you use an algorithm, you are reinventing it to be guaranteed. What we're arguing about is that greater intentionality and reflexivity can be practiced in this as well as other realms. All right. I'll generally be talking about the politics or the ethics. In the Kramer article that we'll talk more about in detail later, he'll talk about value ladenness, that the process that I was talking about in the last slide, by which the selection of or the production of an algorithm is one option among many. That means that what Kramer and his co-authors argue is that means you're actually placing or ladening, you're loading the algorithm with a value-based decision. You decide speed is important, you decide something else is important, you are deciding something else is not important. And the nature of that selection process means that there is a adherence, a stickiness to the values. They do not go away. And in fact, even if your values change, even if you are unaware of it, what you're doing is ladening or piling on values. And this is one of the things that we often have trouble with technologies. Earlier in the semester, we talk about automation in talking about one of the cases in the Winner article. And I say one of the difficulties is that the challenge of automation is that you can never get rid of. It is always laden in this language with the fact that automation replaces labor. It's the basic goal of automation. And in fact, because we live in a situation where somebody owns stuff, all automation concentrates wealth because you're taking the ability to do work that many people had and you're putting it in one place, owned by one person. And those are both very specific issues that have value decisions, choices in them. Automation increases productivity, but it may also, because of that, by contrast, replace prior forms of work, decrease visibility and flexibility of decision making. It stabilizes and standardizes the results. So, for instance, automation replaces what's often referred to as artisanal or craftsman production. And that means that each object produced is similar or the same, as opposed to a craftsman who tailors each one to multiple needs. And the challenge of automation is not to say that automation is bad. It's simply to say that it has positive and negative outcomes. And like anything else, algorithms are in fact a form of automation. Instead of having to determine complex, broad, messy things, you establish a set of rules prior to each instance. And this is really a continuation of the forms of technological politics we've talked about before: digitization, the network expansion, and informationalizing from the internet. Um, that is a really good example of the expansion of scale. And we've talked about the aggregate scale issues since we read Matheson Gray at the beginning of the semester. Um, but it is worth keeping in mind. So today's example that we'll get to is these MRIs, which are devices that allow doctors and radiologists, technicians to look inside the body. But I want to start with a much simpler example of value ladenness. The language Turkish does not have gendered pronouns. Sorry, it does not have gendering of jobs, of nouns. It is not gendered the way that. So, for instance, in Spanish, a cook is male or female. A dog walker is male or female. A doctor is male or female, because the word itself is gendered. And that the nature of gendering can either be that internal gendering. It doesn't really matter if a man or a woman is a doctor. The gendered conception of the word is different from the gendered presence in reality or the gendering of the grammar underneath it. And so, for example, in Turkish, while a man or a woman would be referred to as he or she, there's nothing about saying a doctor or a nurse or an engineer that tells you whether you should be referring to it in male or female. And so, for example, as an example of the value ladenness of technologies and of algorithms in particular, when Google Translate was designed, they didn't only tell it to use direct programmable gendered pronouns, so he, she, it, they. The programmers had a selection process introduced that used best guesses based on value judgments of the culture for the language. So in the modern day, it's incredibly problematic that no matter which language from a non-gendered language you translate into English, the language will be translated into a gendered form. And that's particularly problematic because technically it would not be necessary to gender. And we don't know the context. We don't know if the man or a woman is a cook. We don't know if the cook is a man or a woman because of the translation. We would need other context clues. And if you look at that little still image there, the nature of this is a little bit dramatic. The Turkish, to be able to say she is a cook, is just that person is a cook. It doesn't say she. The Turkish, to be able to say that person is an engineer, just says that person is an engineer. It doesn't say he is an engineer. In translation, the algorithm automatically inserts an expectation about who is likely to use that technology, use that profession, to be that person. And it is a weird thing that Google decided to do, but importantly, it is something that Google has defended as being part of the important processes that this does, despite being sexist. So I want you to look at that and try and understand that that is a direct result of structures within the algorithm used to translate, and it's intentional. All right, so moving from the general discussion and the example of Google Translate, I want you to think this is not a silly little issue. We build algorithms to produce incredibly broad and wide-ranging effects. And one example of that is that Virginia Eubanks who's an anthropologist and a practitioner of field research around issues of technology and how it affects poor people in the United States, in the book Automating Inequality, has shown that in a desire for efficiency and rationalization of the social services industry, we've increasingly demanded the use of computer choice determining software. And the end result of that is that much of how people receive their WIC and food stamps or their other form of human suffering need relief from the government, which is a legally defined right, is actually determined by those computer software algorithms. And one particular example of this that she uses in the book and then in writing about it since is there's actually a set of choice-based decisions that are enacted by people when, for instance, you talk on the phone to people in Pennsylvania where she was working. They have to follow a script, and if you hint at any of those components that certain things are wrong, for instance, if you say that you had to leave your kid home once, if you say the kid was playing outside without supervision, there's a script that requires them to then file a report that the child is neglected, even if it's obvious the person doesn't mean they're neglecting their child. And so one of the things that happens is the greater the expectation that these algorithms are being used on the software side, we actually find that other forms of activity, other patterns of behavior, much like we saw with the mental model issue, other things begin to imitate this pattern of algorithms. And in the case of social services software and social services processes, whether they're being done by computers or whether they're being done by people on the phone, the nature of it is algorithmic. It demands that if this input is produced, this output is produced without recognition or response to context. And this is literally sending people to prison. It is demonstrably both racist and sexist in how it's been designed, in part because most of the time the people designing the algorithms had different perspectives than the people who needed the help most. And I like in one of the articles talking about this, Eubanks quotes from a data scientist who works on large data set math and how to build algorithms to make sense of things in AI, who says models are opinions embedded in mathematics. And that's a really nice way of saying this. And it returns us to this week's central theoretical point that an algorithm is a selected, a chosen way to answer a process. And in doing that selection, you are placing, whether you want to talk about it as politics or value ladenness, into that algorithm. One of the elements that was introduced on the second slide when I said the general issues that we're talking about is that because of the perception of neutrality and because the inherent functioning of software within computers being hard to see, we often can fail to recognize that this is a big legal and ethical issue. And so what's presented here is a one paragraph summary talking about Mark Walport, who's a computer science expert, and he's an advisor to the British government on issues related to it. And he's really concerned because what ends up happening with large data sets, AI and deep learning, is that their entire purpose is to be able to ask questions about the world that we did not have access to the answers to before. And his argument here is that in many cases, large governments, large corporations, the people who have access to these large computing technologies would not have a right or appropriate access to the information that they can get through normal channels. And he particularly is interested, because he is working with the government, to say there are specifically required warrants and legal frameworks for the government to get certain information. And because large data set AI processing now allows you to do that sort of data gathering by inference, so you don't have to ask the question to the person you're asking about, you can ask separately, that this means that there is no transparency and there is no honesty about it unless you add those things in. And in particular, he's interested in maintaining and consistency with the concept of informed consent and consent. That if information is to be gathered, some form of consent has to be added. But the more powerful these algorithms and systems get, the less that informed consent, or even just consent, is actually meaningfully necessary from the programming end. And so his concern is that the nature of the information accessibility that these technologies provide and the invisibility of that processing may challenge us in a number of ethical ways around issues of consent. And I'll use two examples. One of them on the slide is that there's actually a university program which is working on large data sets to do facial recognition, where they've done 75 to 80% success rate, and that's pretty good for this, where without any other information they can identify people who are homosexual. And one of the amazing things about this is that the argument is that, in fact, it's illegal in the United States, where this research is done, for an employer to ask what your sexual orientation is, because it has no bearing on work. But it is also entirely possible, once this software is developed, for employers to use this, and there's no legal requirement that you reveal what sort of data processing you've done with computers. And so there's a fundamental challenge there in maintaining a protection and rights that were established under law. And while the Kosinski and Wang use to talk about sexual orientation is still probably years off, in the United States, there have been 6 major legal trials, all of which have failed against Amazon, Amazon or Google, which centered around the fact that their large data sets were able to infer from buying patterns of other people when people were pregnant. In all 6 cases, it was a woman. In several of the cases, they advertised and congratulated the person on a pregnancy that they were not publicly discussing, and that was the general issue of all 6 cases. But in one case, the computer informed people in the social network of her pregnancy without her being able to tell them not to, because there was no mechanism to respond to the algorithms that were determining advertisements. And in effect, by the algorithm allowing the advertisement saying, hey, one of your friends is pregnant, look at that, the person was then murdered by an ex-boyfriend. And while the courts determined that this was not a legally binding, legally punishable offense, from an ethical standpoint, we get to be a little more strict than that. The direct cause of somebody dying was a technology that followed the orders that were built into it. And I use this as the extreme example because one of the real questions about this is, as we build more and more technologies that naturalize more and more ability to play with and infer from large data sets, we lose certain kinds of privacy. And in particular, we do that without ever actually having a debate about it. We have no transparency of process because the nature of these algorithms, of large data set processing, of AIs, and in some ways, especially of deep learning, become extraordinarily difficult to understand. And the real joke of it is that a couple of years ago, the programmers at Google were asked about one of their deep learning initiatives that was improving people's searches and was apparently giving some negative results while also giving accurate results the rest of the time. And when asked which algorithms might be fixed, they literally couldn't tell them. The programmers at Google, because deep learning processes were allowing the computer to write its own algorithms, we literally could not stop without taking that whole segment down. And in the end, they did. They took out that whole section of the processing for searches, and later determined that the ones that were promoting bad stuff were recognizable and modifiable. But the the problem of transparency, of understanding process and therefore reflexivity, which is thinking about and determining if that process is correct, is just very difficult when you're taking the entire process and putting it into algorithms and distinguishing it from the outcome in such a dramatic way. So algorithms are one of the most important forms of automation in the world today, and we get the article by Knight that asks, in a very simple way, is automation going to decimate white-collar jobs? And for anybody who doesn't know, we traditionally, historically, the term white-collar versus blue-collar derives from if you were earning enough money to have your collars, your clothes laundered regularly, you could afford to have a white-collared shirt as opposed to a collar on your shirt that was a different color. If you had a white collar and you couldn't afford to have it laundered often, you looked dirty. And so there really was a point in history, really mostly between the 1850s and the 1920s to 30s, where this was not just an idiom, a linguistic trivia, but a real description of the working clothing patterns for most of Western Europe and the United States. But it has still become maintained as a language to talk about the distinction between intellectual and creative class jobs, those are white collar, and working class jobs that tend to involve physical presence. And while 100 years ago, blue collar jobs were almost entirely agricultural, and 70, 80 years ago, they were almost entirely manufacturing, the reality of today is that the majority of blue collar jobs are service industry jobs. And in some cases, in some ways, that means that they are safer until we have full mobile robots from automation than many kinds of white collar jobs. And because of the tendency of these things, what we end up with is, in reality, right now, we're at a point where the kind of jobs that are being looked at for automation include things like engineering, web design, and things like that, which are, the phrase is, rote activities. You are often performing the same task more than once, even though it is an intellectual or creative job. And in Knight's article, he's talking to Kai-Fu Lee, who's the head of Google's subsidiary separate company in China. And they're talking a little about the distinctions between China and the US and the way technology plays out. But in central part, what they're talking about is that we're moving to a stage where these new, more complex forms of algorithm-based software can do different things. And they talk about the fact that there have been waves of artificial intelligence, waves of AI, and that there was a big one, which was particularly necessary in moving us to the next ones, of big tag data. And so for a long time, the majority of the large deep learning AIs were about figuring out patterns and usage for social and public databases, things like what Facebook does. But as we got good at that, and more importantly, in some ways, as we determined that the algorithms and software components necessary to do this were well understood and decreased the price, we increased the frequency in a second wave, that workflow and automatable knowledge business tasks were to be based on workplace data. And so because we were getting used to and suddenly had the tools to evaluate large data sets for inferences and patterns and make decisions based on it, it turns out that, for instance, how bankers work, how engineers work, how actual tasks within a job are done are measurable as data. And before you forget, remember, whenever you datafy something, you're erasing a certain amount of context and detail and standardizing it. So while we can recognize that these workflow and automatable knowledge tasks are um, they're limited in how they're framing what you do. They're erasing creativity in favor of outcomes that are expected or processes that are repeatable, but they are in fact able to break down complex tasks like engineering or coding into things that the computer can teach us how to design um, or people can design a process while the computer can establish a set of algorithms to do those things. And as we get better at that, it turns out that um, more and more complex tasks are able to be accomplished in that way. And so we begin to see a third wave now where new applications um, will be in fields where we have to gather new data. And there's been this last 5 to 10 years, as this third wave has begun to start to come about, where more and more data sets are being created in the hopes of being able to produce algorithms and automation for more and more tasks. And one of the real clear examples in the recent years is the deep fakes process to apply a visual filter that moves, effectively a form of animation, using photographs onto a moving image used to be an extremely slow and professional, complex creative task. And basically, a group of fanboys developed a set of algorithms that could match link points to be able to put anybody's face onto any video, anybody's identifying characteristics, anything that was measurable instead of in a picture or in a video of link points. Um, the computer could do all the work of figuring out how to balance and line up all the elements. And so what you end up with is that as people got larger data sets, as people understood the algorithms that had come out of analyzing previous large data sets, we see different data being used and different contexts being approached. And so in wave three, as we've been exploring all these new tasks as automatable, it's really legitimized and created the reality of other forms of automation. And so for Kai-Fu in Knight's article, he says, this is really why people, for the first time, take seriously the near future possibility of self-driving cars and other forms of large-scale robotics and automation. That the ability to see complex tasks as we've gotten better and better at breaking complex tasks into algorithms um, is literally one of saying these are no longer more complicated or complex than the processing power and the algorithms we have done. And whether you're talking about something like traditional Turing tests or self-driving cars, this is a very real approach that we're going to see in the near future, he says. And will automation decimate white-collar jobs? In the end, they don't really answer it. What they do say is they certainly have the capacity to take on jobs that we thought of as being good jobs. And it's one of the things that the article by Knight is saying all the kids who are getting programming degrees, all the kids who are getting engineering degrees, all the kids who are doing these tasks, educating themselves in these because they think these are safe long-term employment opportunities. That's potentially wrong because how we choose what jobs to automate is in part dependent on which things we are able to automate. And 100 years ago, that was automating farming. 90, 70 years ago, that was automating manufacturing. 40 years ago, that was automating service work from some elements like ATMs and secretarial work. And that one of the things that we can consider is that if we are moving towards automation of other jobs, that really has historically eliminated the kind of work that was to be replaced. So let's take a step back from what's in the Knight article to answer those questions. And the simple answer is yes. Continuing automation will destroy white collar jobs. And the real question is whether or not those are the jobs that we want to protect. And we have choices because, A, as members of a society that is governed by law for social benefit, we could choose to protect certain jobs or not. And you can see that debate around issues like the automation of mining and the protection of jobs in the coal industry in the last, 3 to 10 years, first under Obama, in fact, and then under Trump. We can see the increased use of automation attacking the rights of teachers as more and more educational materials are available and the processing of educational materials, things like automated grading, are being done online. We've actually seen a decrease in the quality of jobs for teachers. And that's just very recently that those systems of technology, for instance, real language processing for computers, has allowed them to approach teaching and some other jobs as automatable. And it may be that you don't want to be a teacher. So the question is, in some ways, what about other kinds of jobs? In the two charts that you'll see here, one is about the nature of high-skilled and low-skilled wages. And so something like technical professions, technicians, engineers, we actually can see it's the green and blue bars are the changes in full-time wages between 1979 and 1989. And then between 1989 and 1999, we can see technicians and professionals have dropped dramatically. And believe it or not, there is a whole lot of stuff. There are tons of factors that affect that, but one of the central factors here is increasing competition for de-skilled work. And that is, we produce more people who are more able to do more different parts of that job, in part because components of the job are more and more reliant on technology. And centrally, for many fields, the technology that we're relying on is software. So, for instance, if you look at the professionals category there, where the most recent 2007 to 2012 salary growth chart is actually negative, way down there, part of what feeds into that is things like the decrease in pay for engineers and for nurses as software products like AutoCAD and like the Epic and decision management systems for hospitals have meant that they can no longer argue that their skills should be paid well. And it's a process that has, de-skilling and economic change is a pretty widely established and well-studied thing. And by contrast, or a slightly different way of thinking about that is, um, do you think that in a competitive labor market, having your job, something that you can do because of something you know, or something you can do because you know how to use a tool, one or the other of those is easier to handle? Your knowledge, as opposed to your ability to use a tool that somebody else owns, which of those sounds like you're likely to get a stable long-term paycheck? Well, it's easier to train and find somebody else who knows how to use those software packages. And so the smarter the software gets, we tend to see this pattern of wages. Um, by contrast, we can do direct automation studies. So the chart on the right is a direct study that looks at the relationship between automation's presence in a field and the amount of workers in it. And there's a pretty significant, although not nearly as significant as I expected when I looked up this chart, change that as automation increases, we do see a drop. And it is worth noting that this is this is a growth field, right? We're talking about information technology workers and stuff in this chart only. And so it would be likely that this is a less dramatic version than would happen in some fields as automation came in. So, what does that actually mean? Well, here's the thing. It doesn't mean one thing. It means a lot of different things. McKinsey did a big study. It is one of the more pessimistic. They're a big data processing and polling firm. And they estimate, in fact, that somewhere between 32 and 40 million Americans will effectively lose their jobs in the next 10 years, in large part because of automation. And some of that is about reinvestment and redevelopment of the economic models. And please be aware that doesn't mean 40 billion people will lose their jobs and there'll be 40 million new jobs. Historically, less than a third of the jobs lost to automation are reproduced. So that means that over a long enough period of time, that two-thirds who are absolutely lost jobs may be regained, but we don't see that as a historical pattern. But a big part of what's going on in any of these cases is not the raw data that McKinsey are talking about. In Sweden, where there is a strong government system for mutual benefit, a utilitarian system that has produced a social safety net, where, for instance, if people lose their job, they don't have to worry about losing their houses because unemployment is protection against failure to pay mortgage. You're going to have food. You're going to have health care. You don't have to worry in some ways. And so there's this amazing quote where Goodman is talking to somebody in the New York Times, and he's talking to an expert on Swedish policy, and they're like, a good safety net is good for innovation, right? That literally the only way that Amazon in the United States can function at the moment is because they can pay their workers so little because those workers can get food stamps. And before you're surprised by that, remember that less than 1 in 100 workers who is involved in Amazon is a programmer getting paid well. The other 99% are subcontractors and external people who work in the shipping and processing programs, and almost all of whom are paid very low wages with minimal benefits. And it's a really different thing to talk about automation in the context of Amazon in the United States or in Sweden, where those ethical effects, the harms for individuals, are moderated by context and system effects. And we're talking about a very complicated interplay of multiple choices that is not one or the other. It is not a binary choice. And so how we move forward and conceive of the politics of automation will be context dependent in any case. Labor economics is incredibly difficult, but the real question of what we will do is not just about automation. For instance, if you decide that automation is necessary and you have a reason for that, if you can say ethically, I'm in favor of the nature of automation because this is why. Not because it's innovation and there is something inherently and naturally thing. You need to have a warrant. And so, for instance, in Sweden, where they have this warrant of general good, they can provide for everybody better. They allow automation, they perform innovation because the result is general welfare benefit. And it may be that in the United States, where we have a system directly warranted by individual wealth and individual benefit, you may decide that you are okay causing people to be poorer, cutting people out of the job market. But you're never going to be able to divorce those components from automation in general. Now, while Knight is talking about automation in general, Seidel asked the question, can computers be racist? And this is not Not as silly a question as some people think, because in fact, when people make those choices about what goes into the program, how the algorithm will work, language choice, production choice, function choice, the choice of steps, which things are left out as its data is produced, all have real effects. And if, for instance, the folks who are doing that programming all come from suburban backgrounds as opposed to the country, or everybody, a significant portion of them are male instead of female, we tend to see bias creep in. And when we talked about alternative design, we talked about this ability of the gender or race or other general governing mentalities to be embedded into technology. And we used then the example of the microwave and the way that the assumption that men didn't need to learn to cook changed and was reinforced by microwaves. Um, and here, Seidel is asking, well, if systems replicate and enhance unconscious or untalked about biases, then that's really a way to talk about racism. And racism is just a systematic bias, right? It is structured and structuring of outcomes, right? We're not talking about prejudice. Prejudice is a belief, is a personal bias. Racism is any kind of structural response that produces a systematic bias. And so we can really distinguish between, we're not asking you to think that computers are personally prejudiced. We're asking if some forms of technology, some computers, some software, could be racist. Right? So developers code, they integrate data, the system parameters are determined, and an AI self-determines those things, which can be a problem all its own. Um, all opportunity for negative effects to aggregate or to arise, right? Um, and we can think about a lot of different examples of this. I often talk about one example of this being the background assumptions of the people designing technology often produce politics. Not because the product has a personal prejudice, but for instance, the first generation of those soap dispensers and automatic faucets in bathrooms had been designed by folks who used light sensors, needed a fairly high degree of light change, and it turned out that darker skin didn't set them off. And so there used to be a lot of jokes in pop culture about these water fountains or lamps or the lights turning off in the room because the people inside were black. And that's based on a very real series of incidents. Um, Similarly, police body cameras, which are seen as being useful and for transparency, actually often produce negative effects because the reality is that if there are cultural biases among people around the technology has a tendency to reinforce them. And one of the classic examples of this is police cameras are from the perspective of the person who is wearing them. That's the built-in tech. And that means that we tend to find that there is a real effect of this. And lots of examples. Movie recommendations on Netflix are racially coded because they have been told that individuals in the population tend to be able to divide by race. And interestingly, we tend to think of things like Amazon and Netflix recommendations as about your past history, but the algorithms are actually built based on identity categories that the designers thought were important prior to any individual data. So lots of things end up including categories of race that could be. And Seidel is curious, does this make computers racist? All right, so Seidel is really talking about the fact that we tend to forgive computers. We tend to think of them as neutral, and we tend to consider them outside of a system like racism because we misinterpret or we misremember that racism is about structural effect of uneven bias. It's about discrimination. And that's a different thing than prejudice. A person, a computer, an algorithm may have discriminatory effect. Um, and that what we're really talking about is that we tend to see technology as distinct and disconnected from social realities. And I like this quote from Dr. Randatsuki. He is talking about robots and about artificial intelligence. And he wants to drive home the point that we tend to forget that this is not about a pure technology. It is not disconnected. It is defined by, made meaningful by the relationships and systems into which it is operating. And I want you to really keep that in mind, that the question of if computers can be racist in the same way the IBM computers in the discussion of IBM and the Holocaust, the computers, you don't necessarily have to magically think the computers were doing something evil. But if in context the effect of those computers were bad, it were something you disagree with, to pretend that the computers were uninvolved and neutral is a failing of logic, let alone ethics. Um, there needs to be, as Atsuki says, a question, a demand, a requirement that programmers and hardware engineers, not to mention people who gather the raw material that make the AI and software work, um, that we continue following connections, relationships, we inevitably find troubling images. The the example that he goes on to talk about is that we tend to forget that the actual hardware comes from someplace, but um, the details, the mechanisms of the computer, whether it's algorithms or otherwise, thinking about where they come from, who they're meant to serve, who profits, who is harmed, all of the politics of it, is a really necessary way to understand these things. So I can't remember if I've already talked to you guys about ATMs, and one of the real sad things to me, because I think ATMs are a great convenience technology, is that we tend to forget that ATMs replaced what was a very different job than the one that we see tellers doing now, where tellers are effectively glorified service workers. They're service workers who handle money instead of handing you a plate at a restaurant, but there is no longer the social role that considers them real bank employees. And one of the things that's lost historically is that bank tellers who were replaced by ATMs are historically one of the main avenues for working class and people of color to become knowledgeable about banks, to be educated and trained in finance. And so I use the example of ATMs, but I wanted to mention this Alex Madrigal article where he talks very specifically about the same worry is happening now, that metropolitan train and bus drivers for transit authorities across the country um, tended, because of the history of that industry, to be a good middle class job that was available for working class people and particularly people of color. And there is a real problem if we replace somewhere between 6 and 10 million people who have good middle class jobs with automated trains or with self-driving buses, because there are fewer and fewer of those opportunities for advancement and promotion into stable economic life left in society. And when we talk about computers being racist, I want you to understand one of the things that is in the background of that is that when we use algorithms, when we use neutral sounding processes as an explanation, even something as simple as an algorithm, What we're often erasing is secondary effects are unseen political elements. All right, so all of you should have read the Kramer article, and it is the ethics in an algorithm. And its focus is on how the determinations of how you program an MRI machine, what the actual algorithms are, what the consistent effects of that are, produce ethical outcomes. And the framework to consider is, Kramer argues, the value ladenness of those algorithms, that they are not neutral. The choice of which algorithm or which way to design the algorithm has to be determined by values. There is no absolute objective right answer. In fact, there can't be an objective right answer. You have to use a value or a ethics determination. And therefore, this is an example of value-laden processes or value-laden decision-making. Algorithms cannot be designed without taking a stand or determining, as the designer, which value to uphold. And they're particularly interested that there are implicit and explicit decision-making going on here. So in some cases, the decision you make is one that you realize is a decision. In some cases, you sort of don't. And some of that implicit and explicit distinction is important because it changes what the transparency is. And in the end, we come to some of the same concerns that we saw in the Miller article about the tunnel problem, where he comes down on the side of informed consent. His argument being that in conditions when a value-laden decision is being made, it may not be appropriate for the designer to be the one doing that. And while he was thinking theoretically about this in the case of self-driving cars, Kramer and his co-authors are talking about this in a very specific and real case. And the case has to do with how MRI machines determine when to say they have seen something. Now, the nature of an MRI machine, and I thought about putting one here, but I think most of you have seen one on TV. It's a tube you stick a body part or a person in, and it uses magnets to see what's inside the person. And the way it does that is not by producing an image. It's not an X-ray. It's a digital process. And in effect, it takes a series of magnetic pushes against the thing. And depending on the density of the thing that's inside it, it can tell what the amount of magnetic force is hitting the other side. And all you really are getting out of the MRI machine is a series of numbers. Those numbers are the variations in how much magnetic energy appears at the sensor on the other side. And what the algorithms built into the processing unit do is figure out how to represent that in 3 dimensions by connecting a lot of those different measurements. And the core question at the center of this case that Kramer and them are talking about is that the degree to which that variation matters can be interpreted in lots of ways, and it's actually very complicated. But we're going to use this example in a simplified form. If you look at that little chart, this is representing how to show the difference. And the line that sort of squiggles across and has a hump, almost like a curve, like not quite a bell curve, is a representation of the energy being produced, right, of the amount of measured variation. So as you move across this location system, each of these points would be a different measurement. And you can see that there's certainly a difference between the top of the hump and those deep troughs, the bottom pieces on the right and left. And their argument is that in some cases, that would be even very explicit, but because that very sloped side is there, somebody has to decide between what are marked as value 1 and value 2. Which of those is the marker? Because it's either going to show a larger black dot or a smaller black dot on the MRI. And if it's a larger black dot, well, then you might think it's cancer. If you use the narrower one of those and it's a smaller black dot, people won't think it's cancer, right? These variations and the boundaries where you determine how much information becomes meaningful, what is datafication or datafied, as opposed to disregarded as being static or non-informative. And their argument is that because there are limitations both in technology and in the material realities that we're dealing with, this is something somebody will have to decide, not arbitrarily, but based on their determination, their values. So, for instance, if you look at the picture on the right here, depending on where the line is, that light segment being marked off in red is the machine saying, look, we think that there's something here. If they use the green one, that's a much different line. The nature of MRIs is pretty specific. We don't use MRIs when people are well. We use MRIs when there is a suspicion of an illness, a problem, cancer, or other. And that means that the decision of if you're going to, they call it segmentation, that is variation, which of these decision making is going to be doing it. The decision about whether or not there is going to be a high degree of sensitivity or a low degree of sensitivity means really you're saying, are we working on false positives or false negatives? So, for instance, in general, the scientist would always want false positives. They want more information, and then they can check and keep going. But that's expensive, and it's time wasting. And depending on who you're asking, it's also incredibly harmful for patients to give them lots of false positives because it's terrifying for them. It means that they're less likely to take it seriously the next time. There are all sorts of effects of that. In contrast, doctors in a doctor's office actually prefer false negatives, false positives. They side with the scientists. They'd rather a radiologist come to them and say, it looks like they have cancer, and then go to the patient and scare the shit out of them. Patients are a little more complicated because they would rather have neither one. They want faster information, they want more certainty, and they don't want to be scared. Different groups then interpret that differently, but none of those groups are the ones who are actually designing this. The programmers who are designing this tend to be designing in a different way. And one of the things Kramer argues is if we think about this as a value-ladenness, if we recognize it, then we can decide if that is the right person, as Miller did, to make that decision. In choosing the threshold, whether that degree of accuracy and precision is going to be for more false positives or more false negatives, there are a lot of options. They could follow an ethical code. They could use a precautionary principle, which is what doctors will tend to do. They'd rather have more false positives and scare people, but be able to catch more of the cancers. There's a risk positive approach, which tends to favor fewer false positives, being less precise, because that means that you can process more people with the MRI faster. It wastes less money. It gets the whole system going smoother. We could use an industry standards approach, which is a little more difficult because the algorithms are often proprietary. They have to be shown to the government that does regulation for this, but you can't actually expect every different manufacturer of MRI machines to use the same standard. And then there are questions of, well, maybe it is a question of leave it up to somebody else, flexibility or informed consent. But if we're going to end up with fights where, for instance, radiologists versus primary care doctors versus oncologists, all doctors, versus research scientists versus the patients, each one is going to perceive this in a different light. It may not be necessarily ideal to just leave this up to people later. And so this case presents a really difficult but interesting one for us to consider as a way to think about the realities of simple, straightforward ethics being embedded in the machine. In some cases, these machines actually are adjustable. And then one of the fascinating things is because the machine doesn't make it clear that it's adjustable, we maintain that only some people have the ability to do that adjustment. The article takes a stand, but for our take on this case, I want you to focus on the general nature of the case. When determining segmentation or threshold variation, that is it going to fall inside this category, inside that category? We almost always have to have an outside determining factor, a value, what we care about, what we ethically believe. And that means that the decision and the technology that results from that is an ethical thing. It is an example, a pretty specific one, of how politics is embedded into, how the actual, the kind of politics that Winner introduced that we've been talking about all semester, how it gets into a technology. So normally after we go through that, we spend the Thursday talking about engineering ethics and how professional codes of ethics are algorithms. And we compare 4 professional codes: a modern translation version of the Hippocratic Oath for Doctors, the American Medical Association Code of Ethics, the Code for the National Society of Professional Engineers, which is intended to be a very general professional code, versus the IEEE, which is a specific engineering code. IEEE is the electrical engineers. And we talk very specifically about some of those things usually. For example, one of the central points that becomes defining of the modern Hippocratic Oath and that then influences other codes is that the modern Hippocratic Oath lists 2 key ways of doing good. First, not doing harm. And the fancy term for first not doing harm is non-malfeasance. Non-malfeasance. Don't do bad things. And the second way of doing good is to heal, to do good acts. And that one of the things we can talk about in trying to do the in-class exercise we usually do is, does it change what the outcome is, which order those 2 things are in? Right? So if your first directive, if the first step is to try to do good, to try to heal, and then after that, you have the first do no harm. Or, in that case, I guess, second do no harm. Or, to use the traditional Hippocratic formation, which is first do no harm, and then if you think you can act without harming, can you do good? And it's a particularly interesting issue around medicine because lots of forms of medical treatment can potentially have harm. But this is particularly important because this formulation is actually used for lots of professional codes. The code for the National Society of Professional Engineers, to some degree, includes this distinction. Before you ask how you should be an engineer in any specific case, it does basically start by saying, if this isn't going to make the world a better place, you shouldn't be doing it. And so the variations between the codes of ethics and the sequencing and prioritization of kinds of ethical statements in the code makes a difference. So we discussed that, and then I asked you guys to break up and you'll form groups and you actually write out an algorithm to produce an ethical decision. And I'll talk a little more about the codes of ethics in a minute, but usually what this does is it gives you a really specific and focused way of thinking about ethics. We talk a lot in class about reflexivity and intentionality, and it's useful to be specific sometimes. On the midterm, some people chose to answer and often didn't do a very good job. When I said, what are specific rules that you would apply? And people were like, I'm going to do a good job. I'm like, that's not specific. And so when we talk about specific versus not specific, when we talk about prioritization, lots of kinds of thinking through ethics can be done algorithmically. And while we don't actually necessarily want to produce the algorithms, we don't want a stable, absolute, decontextualized version. It is a worthwhile process to think through. So, a long time ago, I'd said later in the semester we would talk about actual engineering ethics codes. And so we will take a minute today, and I recommend all of you go out for whatever field you're in, for whatever profession you're aiming at. You should be able to think about these things. You should know what's in the code of ethics. The NPSE is sort of the neutral. They are the background version that is less divided. Almost any professional engineer, whatever field or variety of engineer, can be a member and potentially should be a member. And the code is broken up into three parts. The preamble, which is placed first, which explains why ethics are important. The fundamental canons, and canons just means they're the things that define it. And believe it or not, the fundamental canons are the warrant for why you have other specific rules, and then after that are rules of practice and specific obligations. And it is worth your time to go through and read those. I will tell you that having now assigned it, the fundamental canons and preamble of the NPSE code could potentially appear on the final. So we'll see. But it is worth knowing what's in those codes because they are the expectation that you should perform. All right, so final thoughts. I want you to understand that when we talk about the value ladenness deriving from the perceptions and way of thinking of the people doing the algorithms, this is a pretty straightforward process. I believe X, I design something based on that belief. Somebody else believes or understands things differently. And so one of those examples could be how you perceive what something should do, how you could conceive of something that is a beneficial thing, or how you think users may want to do something. And this is why we talk about participatory and universal perceptions of design as opposed to using mirror technique, which doesn't question these assumptions. And so I just wanted to give you one other example of this, right? So the question for you is, when you think about thieves, who steals the most? Who is a thief? Who are you imagining? What kind of action? The assumptions and what we're directed to pay attention to, how we think about things, produce the algorithm that we use. And the nature of that is a little bit tricky because, for instance, bosses in the United States steal more than twice what every criminal, the way that you think of criminals, do. And so if theft is about taking what is not yours, then why don't we talk about those things as theft? The algorithm by which we determine criminal activity tends to erase certain kinds of crimes. For instance, stealing $500 on the street, right? Grabbing somebody's purse holds a larger prison sentence, right? This is an algorithm, prison sentencing guidelines. That algorithm gives a longer prison sentence for $500 than it would for embezzling $1 million. Embezzling is a lesser crime in some ways. And the nature of how we conceive of something like crimes or how we imagine people to be is one of the ways that these biases or perceptions produce value-laden technologies. Now, that's the end note. That's it. Sorry, I would give you more on a bunch of these details if we were in class, but for today, that's all. Have a good one. See you on Wednesday or